Hello everybody, so this is the first lecture associated to chapter 3 of the reinforcement learning course. So the purpose of this chapter is to introduce problems that are called Markov decision problems. Okay, so we'll study concepts associated with these types of problems. And why do we study that? It's because reinforcement learning methods have mainly been developed to tackle these types of problems. Okay, so we will discuss the problems and discuss challenges associated with the solution of those problems. Okay, so this chapter covers chapter 3 from the Sutton and Bartow textbook, the second edition. Okay, so Markov decision processes, okay, so P can be problems or processes. They are frameworks where we have an actor or an entity which attempts, or also it can be called an agent. The agent attempts performing a sequence of action so as to optimize a sequence of rewards he or she obtains. Okay, so we can see already parallels with what we've seen in chapter 2, but we are going to see what the Markov decision problem setting is much more general than what we studied in chapter 2. So, in particular, one difference is that the Markov decision problem, I'm going to use MDP here. So here it can be Markov decision process, Markov decision problem, both are fine. These problems, they generalize the K-arm bandits first by introducing associativity. Okay, so in these problems, there are typically more than one state. There are many possible states of the nature, and then the optimal actions are functions of these states. Okay, so the best action, there's no single best action which is universally the best all the time. The best action depends on the context in which you're in. Furthermore, another key difference between the more general MDP framework we're going to discuss here in comparison to what we've discussed in chapter 2 is that um, every time you take an action, the action will influence the likelihood or the probability associated with your next state of the nature at the next time step. Okay, so in the armed bandit, when you take an action, you receive a reward. Then you go on to the next time step, and what happens in the next time step is just independent of what happened in the previous one. But here in the Markov decision problem, at each time step, we're gonna be in different states. But every time you make an action, this influences the likelihood of falling in the different states in the next step. Okay, so this is another generalization in comparison to the bandits framework. We're going to discuss that some more, so if this seems a bit abstract right now, this should become a bit more concrete shortly. So, Markov decision processes or problems, they involve the following. They involve a set of time points. So sometimes these are called stages. So here the time points are denoted with that fancy T, which is the set of all time points in the process. So here T is here we use discrete time points. So T is equal to 0, 1, 2, 3, 4, 5, 6, 7, etc. The frameworks also involve a set of possible states of the nature, a set of possible actions, a set of possible rewards, and here a function p which characterizes the evolution of states and rewards in the procedure. Okay, so this how do these elements relate together? We'll explain that shortly. Okay, one quick detail: if all the following are finite. So the set of possible states, the set of possible actions, and the set of possible rewards, if they all are finite sets, then we say that the MDP is a finite MDP. Okay, so finite means that there's a finite number of outcomes among the possible ones. Okay, so how do Markov decision problems work? Well, so as we mentioned earlier, this is a sequential decision problem, so there are many time steps, and then at any time step t, at the beginning of the time step or the stage, you're in some state called st. So st is the stage in which you're in at time t, which is among the set of all possible states. Then once you're in state st, you take an action at from the set of all possible actions. So once you or the agent takes an action, then the agent receives a reward rt plus 1 just before reaching the next time step. So at time t plus 1, the agent will receive a reward. That reward it can be either random or deterministic based on your action and your current state. And then once you receive a reward, you transition randomly into a next state at the next time step. Okay, so here we say randomly. For some problems, there are deterministic transitions, but these are a particular case of the random transitions framework. Okay, so we can study the random transitions framework, and then we can cover also the deterministic case here. Okay, so if we recap, Markov decision problems or process looks like the following. Okay, so you start in a state as 0. You are, let's say, the agent. So the agent starts in a state as 0, performs an action A0, then receives a reward which is influenced by both the state and the action in which the agent was. So at time 1 it receives a reward and then transitions into some state S1. Then in the state S1, the agent chooses an action, receives a reward, and then transitions into a next state. And etc. It continues like this. Okay? So you're in a state, you take an action, you receive a reward, then go into the next state. Then in the next state, you take an action, receive a reward, transition into the next state, etc. So in the case of a finite MDP, so if we have a finite possible number of actions, states, and rewards, then the distribution of all these quantities is characterized by a probability mass. Okay, so if there's a finite number of actions and states and rewards, then these are discrete random variables. Okay, so we can characterize their evolution according to the function p, which we call the transition function earlier. Okay, so here p is defined as following. Okay, so in these types of problems, we have that the probability of reaching a state S prime at the next time step and receiving a reward R at the next time step, given you're in state S right now and you perform an action A, and you know also all previous states. So S1 at 2 points t minus 1, it means all states from time 1 until t minus 1. Okay, so this is denoted below. So x1 to t minus 1 denotes the sequence of x1 until xt minus 1. And all possible actions here. Okay, so let's just recap that part. So the probability of going into state S prime and receiving a reward R if you're in current state S and you do perform the action A, and also given all previous states and all previous rewards, and by previous I miss before time t, is determined here by that function, which is denoted PS prime R S A. Okay, so a first thing we notice here is that all states before T and all actions before T, they're not in the right side here. Okay, so what this means is that in these types of problems, the only thing that matters to determine the distribution of the next reward in the next state is your current state and your current actions. Okay, so all previous states and all previous actions, they have no impact on determining what's the next state and next reward. Okay, the only thing that matters to determine these is your current state and your current action. So here this function P determines the distribution of your next state and next reward given the current state you're in right now and given the action you take. Okay, so this notion that the only thing that matters is the current information to determine your subsequent state and reward and not the previous information. So this is referred to as the Markov property. Okay, so for those who never saw what Markov chains are, I encourage you to read. I've put a set of slides online which are a primer about Markov chains. So if you were never exposed to Markov chains in your previous classes, I highly recommend you read these. Okay, so the function P characterizes the evolution of the system. It tells you if you're in a state S right now and you take an action A, what's the probability of landing in the next state S prime and receiving a reward R. So because P is a probability function, then if you sum all its arguments on the left side, then this must sum to 1. Okay, so if you sum across all possible next states and all rewards of the conditional distribution of the next state and the next reward given current state and action, then this of course must sum to 1. Okay, so these transition probabilities, they are probabilities. So as we know, when we sum all elements of a mass function of a random variable, this must sum to 1. Furthermore, one other thing we didn't mention yet is that this quantity here, there's no t inside. So let's go back one slide. On the right side, there's no t appearing, even though it appears on the left side. Okay, it means that at all time steps, we assume that these transition probabilities are exactly identical. Okay, so for that reason, we say that transition probabilities are time homogeneous in these frameworks. Okay, so time it doesn't matter where you are, at which stage you are. At all stages or time points, you always have exactly the same transition probabilities. This is our assumption. Of course, everything. Of course, I mean, I'm telling you, everything that we do here could be generalized to non-time homogeneous probabilities. Okay. However, to make the exposition more simple, and because there are many time homogeneous problems in practice, we will only restrict ourselves to time homogeneous problems. Okay, so we've defined the transition function P. What are the possible information we can get from that transition probability? Okay, so here in this slide we show that this allows you to get other information. Okay, so once you know the transition function P, you can get the following information. Okay, so the first thing you can know is the state transition probability. Okay, so here, if we go at the right side, let's assume we know that probability to transition in a state S prime and a reward R. Then what we can do, we can sum over all possible rewards R, and this becomes the probability of transition into a state S prime given current state S and current reward A. Okay, so this is defined like this. So if we know the transition function P, we can know the state transition probabilities, which are probabilities to go from one state to another given a current action A that you take. A second piece of information we can get if we want is the expected next reward. Okay, so we can define RSA as the expected reward we will obtain at the next time step given our current state and current action. And this, of course, we can simply use rules of conditional expectations to obtain that. So this simply entails it's an expectation over reward. So you sum over all possible rewards times. So maybe I'll write this. Where's my pen? So here, this should be RSA. Okay, so here I use a bit of abusive notation. Same thing here. So here we still use the function P even though there's a single input to the function, whereas P was defined as a function with two inputs on the left side. Okay, so using the same P here and here, it's a bit of abuse of notation, but because it's clear in the context what we mean, we're gonna accept this abuse of notation. Okay, so here when we want to know the conditional expected reward given the current state and current action, it should be the sum of all rewards, possible rewards, times the conditional probability of obtaining such reward given the current information. Okay, but to obtain this probability, you can simply take the transition function and sum over all possible states S prime to get this. Okay, so this gives us the expected reward for the next step, conditional on current state and current action. Furthermore, another quantity we can get is the following. It's the expected current reward. Okay, so here this was the current expected next reward at the next time point. We can also have a current expected reward, which is let's assume that we're already at time t plus 1. We want to know what's the expected reward we will get given at the last step we were in state S, that we performed action A, and then now that we transition into state S prime. Okay, so sometimes it can be interesting to have this quantity. Well, this is simply, again, it's a conditional expectation of the reward. So you sum over all possible values of the reward, then it should be times P R given S prime S A. And then this probability here, you can simply decompose it as the following. Okay, so when we have, recall the rule, when we have P A given B is equal to, or okay, I'll add this, P A B C is equal to P A B given C divided by P B given C. Okay, so we can use this rule here to show that this probability here can be written as follows. Okay, so if you let C is equal to SA, then you can decompose this as this here. Okay, so this shows the transition function not only characterizes the evolution of our system, but it also provides interesting information about the rewards and state transition probabilities. Okay. So In practice, for many problems, which we will tackle through reinforcement learning, the transition probability will be unknown. Okay, so for example, if you do some stock trading and you want to optimize your stock trading process, you don't know in practice what are transition probabilities. Okay, so nobody in the world knows what's the probability that the stock will go up tomorrow or go down tomorrow. This is an unknown quantity. Okay, so in practice, for many problems that are of interest, the transition probability is completely unknown. However, there are other problems where the transition probability is known, but the problem is still difficult to solve. Okay, so here we give one example. It's the Rubik cube. So if you try to solve your Rubik cube, it's not an easy problem. There are many techniques to do that, but one of such techniques is reinforcement learning. Okay, so we can use reinforcement learning to try to discover how to solve the Rubik cube. But for this type of problem, the transition probability is known exactly. Okay, so you know exactly if you're in one state, and if you do one action, which is like the state is the location of all the colors in your block, and your action is where you turn the cube. So if you know the state and the action, you know exactly where you will end up. Okay, what's going to be the next configuration of all your colors on your cube. So in that case, this is a problem where transition probabilities are known, but we can still use reinforcement learning to tackle it. Okay, so now let's introduce what we call a terminal state. Okay, so we mentioned our process where you're in a state, you take an action, receive a reward, fall into a next state, next action, next reward, etc. But does this go on eternally, or do you stop at some point? So for many problems, that sequence of state, action, reward will stop at some given point. And to represent that, we assume the existence of what we call an absorbing state, S star. Okay, so S star is defined as a state which is such that once you reach that state, the process ends and you don't receive no further rewards. Okay, so the experience stops at this point. You don't have no more rewards after reaching that absorbing state. Okay, so this absorbing state, S star, it's often referred as the terminal state. So in what follows, if there's some such terminal state, we will denote by T the arrival time to this state. Okay, so capital T, it's the smallest time point for which your state is the absorbing state. Okay, so T is the first time you arrive at that absorbing state, and then we're going to assume that once you reach this state, you can never leave this state. Okay, so you stay there forever and you don't receive any further reward. Okay, so if S is different from S star, the probability to go from state S star to state S will be assumed to be 0. Okay, for any action A, and any S different than S star. So what this means that it's impossible to leave your absorbing state, and furthermore, for all time steps subsequent to the arrival time or to the terminal state, your reward must be equal to 0 with probability 1. Okay, so this is problems where there exists a terminal state. Some problems we're going to see that instead the sequence of state, action, reward will last forever. Okay, so a bit of notation here. So we will sometimes make the following distinction where S plus is the set of all states including the terminal one S star, and S will be the state a set of state excluding S star. Okay, so in the beginning of the chapters, we said S is the set of all states, but sometimes if we add a terminal state, we will call it S plus instead of S. So in an episodic task is defined as a Markov decision problem where the probability of reaching a terminal state eventually is equal to 1. Okay, so you're certain to reach a terminal state at some point. So with probability 1, your procedure of state action reward will end at some point. Okay, so an episodic task is a task for which the absorbing state is certain to be reached eventually. Okay, so now we're going to define the notion of episodes. So for an episodic task, an episode consists in the travel through all the stages or all time steps of the MDP. And all time steps are 0, 1, 2, 3 until capital T. Okay, so the episode is the outcome of going through all time steps of the problem up until you reach the terminal state. Okay, so the episode always starts in an initial state as 0 and finishes in the terminal state S prime. Okay, so typically once the initial state is reached, what's going to happen in practice then, the system is reset and then another episode starts. Okay, so you restart at time 0, then go through all state, action, reward, etc. You reach the terminal state, and then you will restart the process, restart at time 0, go through another episode, and continue like this. Okay, so here T, the time that it takes before reaching the terminal state, is a random variable in that case. Okay, so it will vary from one episode to another. Okay, so for example, if you play chess, an episode would consist in playing one game. Okay, so in chess, as we mentioned, the set of states would be the various possible configurations of the pieces on the board. The actions would be all possible moves you can make. And then the rewards would be 0 all the time, except you would get a reward of 1 if you win the game at some point, and possibly, let's say, -1 if you lose that game. Okay, so here T. Okay, let's discuss that in the next time. Next. Okay, no, it's not written. Okay, so here the absorbing state S star would be a state where you either have a checkmate from your opponent, or either you checkmate your opponent or your opponent checkmates you, or where there's a stalemate. So a stalemate is essentially a draw where nobody wins the game. Okay, so here we can see that capital T, the arrival time, is random in chess because the different games of chess involve a different number of moves before the game ends. Okay, so this I feel illustrates pretty well what is a Markov decision problem. Okay, we've talked about episodic tasks. Conversely, there's also what we call continuing tasks. So continuing tasks are Markov decision problems where either there's no terminal state or there's a probability to never reach that terminal state. Okay, so if the probability of never reaching the terminal state is greater than 0, then the Markov decision problem is referred to a continuing task. Okay, so a continuing task would be a task where there's a non-zero probability that there will be an infinite number of time points, of stages, and you will never reach the terminal state. So an example of such problems in practice, or let's say at least in the literature, because in practice we have finite lives and we don't tend to tackle infinite time problems. But let's say in theory, people have proposed models where you have a portfolio manager investing assets, and they consider an infinite time horizon over which an individual or an entity would maximize his revenue stream. Okay, so for example, if you are a company which has assets to invest, you don't necessarily want uh, to set up a fixed investment horizon. You might want to look beyond that horizon because at that time point there, at any time point, you still will have stockholders which will continue to invest in your stock. So in that case, uh, people have considered portfolio management problems with infinite time horizon. Okay, so here these would be represented as continuing tasks in the according to the reinforcement learning terminology. Okay, so in Markov decision problems, the typical goal of the agent is to maximize the total reward it obtains over the long run. Okay, so the agent does not necessarily want to only to obtain short-term rewards. He typically wants to obtain uh, rewards not only in the short term but also in the long term. And sometimes the long-term rewards are uh, as important than the short-term one. Okay, so when he takes an action, the agent won't necessarily consider only the next step reward, but all the potential stream of actions he will receive subsequently. Okay, so we will introduce more formally what we assume will be the agent's objective in reinforcement learning problems. Okay, so the approach or terminology we will use will be sufficiently general to handle both episodic tasks and continuing tasks. Okay, here I wrote continuous, but I think it's continuing. Okay, so here this continuous, you can replace it with continuing. Okay, so we will the notation will be general enough to handle both types of tasks. So here in the whole course, we will assume that our agent attempts maximizing the expected sum of all future discounted rewards. Okay, so this is a lot of words, but we'll illustrate that right now. So in other words, the agent is assumed to maximize over all possible sequences of actions the expected, here G0, I use G because G can be represented for gains, but here G will be defined as the sum for all future time periods of their rewards, but we will add a discount factor to their rewards. Okay, so rewards in the very long run will be worth less typically than rewards over the very short run. Okay, so here I use G for gains, but in the reinforcement learning terminology, often G is called the returns. Okay, so the return, GT, the return at time T, is the sum of all future rewards where rewards are discounted. Okay, so GT, it's the reward at the next time step plus the discount factor times the reward in 2 steps plus the discount factor to the power 2 times the reward in 3 time steps, etc. Okay, so this goes until infinity. So if we write that more concisely, the return at time t is the sum for all future time steps here, so all possible k, of the discount factor to the power k times the reward at times r plus rt plus k plus 1. Okay, so this is a short way to express that sum here. Okay, and we can just do a change of index. So instead of k starting at 0 and having t plus k here, we can instead write the following. This is the sum for k starts at t plus 1 until infinity of gamma k minus t minus 1 rk. Okay, so this is just rewriting the index in this summation. Okay, so why a discount factor? Well, if we have a continuing task, we typically have a infinite sequence of rewards. So if we sum them without discount factor, these sums will typically diverge. So to ensure we have a convergent sum here, we must assume that the discount factor will be strictly smaller than 1. Okay, so by definition, the discount factor will be between 0 and 1, okay, inclusively, but for continuing tasks, again, this is continuous, but it should be continuing. So for a continuing task, one typically needs strictly smaller than 1 discount factors to ensure that the summation is convergent. And here, why does gamma typically, gamma smaller than 1 ensures convergence? Recall that if we have a finite MDP, then the rewards are bounded by the maximum possible reward. So this summation here, it will be smaller or equal to the sum of gamma k times the maximum reward possible, which is a geometric sum which converges. Okay, conversely, if we have an episodic task, we could still add some discount factor, but in many cases, the discount factor is set to 1. Okay, so when we have an episodic task, it's very typical, and this, in most of the course, we will do that. We will set gamma is equal to 1 for episodic tasks. Okay, so all rewards in the future have equal weight. So in practice, can you still put a discount factor for episodic tasks? The answer is yes. So typically, I have a more financial background. So in finance, you always discount cash flows for the time value of money. So you can still do that, but for the sake of the current course, for episodic tasks, we will typically set a discount factor equals to 1. So if gamma is equal to 1, then the objective of the agent is to the following: to solve across all possible sequences of actions a0 until at minus 1. So recall that capital T is the time at which you reach the terminal state. The expected value of your return, G0, which is the sum of all rewards starting at time 0. Okay, so if the discount factor is equal to 1 in an episodic task, then GT is defined according to the same formula we had previously. But here, two things. Gamma becomes equal to 1, so the gamma disappears here. And then our infinite sum, because all rewards past the arrival time to the terminal state are 0. So the tail of the summation here is a set of 0, 0, 0, 0, 0. So the summation ends at, the last reward is R capital T. So this summation ends at capital T minus 1. Sorry, just to ensure. Okay, I think there's a typo here. So the index here, because here if we replace k by capital T minus 1, there's something problematic. It becomes small t plus capital T, but it should be just capital T. Okay, so this index here, I'm sorry for that. There's a typo. I'll fix it in the slides, so when you print the slides, it's going to be fine. Okay, so we're gonna stop the video today, and then in the next video we'll have some more discussions about Markov decision problems. So have a nice day.